Okay, so 15.4 is on Green's theorem, and then we're going to see sort of analogs of Green's theorem as we move along. So, and look at things in higher dimensions. But Green's theorem essentially translates questions about a line integral to questions about double integrals, or to solving double integrals. We need some definitions first. So when we were looking at curves before, all we really cared about was what that curve was. We were less concerned with how you moved around it. So we're only going to be looking at closed curves in this section. And so the idea is that a closed curve corresponds to a region in the xy plane, right? And for right now, let's assume they don't cross over each other or anything. I just have a simple closed curve like this. Okay. And so you can talk about orientation. And so I'll just say positive orientation. I don't know how much I want to say. I'll just say counterclockwise. It'll get a little bit goofier when you start putting holes in something, but for right now, let's just think of it that way. So this has positive orientation because you're moving around this way. And so when you think of positive orientation, you should just think as you walk along your curve, following the arrows, your region's always off to your left. Okay? So if you follow the direction of it, it's off to the left. All right, and I'll just say if this is some region D, this curve with positive orientation will denote by, it's really the partial derivative symbol, but we say the boundary of D. Okay? So that's what that represents. And whenever you see boundary, that means boundary with the correct orientation, the positive orientation. Okay? All right. And so orientation is a huge and very important thing in topology and in geometry, I guess. I don't know how much I want to say. What's a, so maybe you guys know, what's a non-orientable surface? Something everybody's seen at some point. A surface, so when you think of a curve, right, we say positive orientation, you're moving in one direction. And so for a surface, we say there's an orientation if we can talk about the top and bottom. So if I got a piece of paper like this moving through, I can say this is the top, right? And then this is the bottom. And no matter how I move along the top, I stay on the top. Same thing with a sphere, right? You got a sphere, you're on the outside of the sphere, we'll say that's the top. And you can move around, you stay on the outside of the sphere. Can you think of a surface you've seen before where that's not the case? It's something that everybody does, maybe in elementary school, you create these things. I don't know why, it doesn't really matter, this has absolutely nothing to do with what we're. Where's my, okay. This is a surface. It has a top and a bottom, right? It doesn't matter which one you call it. You could call the top the inside even, but the point is, it's orientable if you stay in one place, right? What if you fold this over? You have a top and a bottom now. Think about my piece of chalk. My piece of chalk starts here, and if I trace around and I stay on this, I end up on the outside, right? So if you do a circle, you kind of hit both sides. So there's no natural way to talk about tops and bottoms of a, what do we call this thing? Everybody know the name?
Piece of paper swirled together.
You've never heard of a Mobius strip? Wow. What are they teaching in schools these days?
I mean, we just make them rings, not like
Yeah.
that, and then connect them together and hang them around the room as decoration.
No, those are different. So that, what if you took that thing and you did 2 twists on it? So there's one twist. If I twist it again, do you think it's orientable or not?
Oriental.
So does it have a natural top and a bottom?
Yes.
Now it does again, right? And so let me just say, you start here you come across, this, you're not gonna be able to follow this, but I come back up like that and I end up back there, right? I don't end up on the back side ever. And so these are really important objects, really important concepts, but we're not gonna worry about them all that much. I've ripped up someone's homework, so somebody doesn't get to do homework today.
Aw.
All right. So anyways, we'll come back to maybe a little bit of that later on as we get into three-dimensional stuff. I just thought it was a reasonable time to mention it. Okay, a definition. So sometimes you'll see the circulation, you'll be asked to compute circulation of a vector field. F on a closed curve is given by. So this is just another way to ask about, another way to ask about this line integral. And you should think here, you know, if you had some object that looked like this, and you had this vector field that went more or less like this, you know, it might do all kinds of other stuff. But you got this vector field going here. Think of this, think of the vector field as like a liquid, and this is your region. And so if you were to travel around this curve, would that vector field help you travel around the curve or oppose you for traveling around the curve? Help or hurt you? Yeah, it's flowing in the same way you're going roughly, right? And so it would help you. And so in that case, you're going to end up with a positive circulation. If it was opposing you, you'd end up with a negative circulation. And then if it's zero, then it sort of helped you in some places, right? And then sort of didn't help you in other places. So let's just do an example. Find circulation of F equals y comma negative x on the boundary of the unit disk. Okay. So let's just look at this. So we want to compute, right, the integral of c dot dr, the boundary of the unit disk. So we're just talking about the unit circle, right? So we're on the unit circle. If we talk about the boundary itself, then that means this is our c. The c is the boundary of this. So we want not just some random orientation of the disk, but the positive orientation, right? So whatever we do for our c, we want to come up with a curve that moves around it counterclockwise. And so which parameterization does that? Cosine t, sine t. If for some reason you were asked to go at negative the boundary, right, so you'd go clockwise, then you could have started with the sine cosine, right? So just be aware that when you swap places, you change the orientation that you're spinning around. And then to go around the circle once, what's our bounds for t? 0 to 2 pi. All right. If this f was conservative, we could use the fundamental theorem, right? So don't be opposed to that. On a closed loop, what's the fundamental theorem always going to give you then? So it's f of your endpoint minus f of your starting point. And so if you're on a closed loop, it's always 0. This isn't a conservative vector field, so you can't do that, but just be aware of that. So we just have to kind of go with brute force here. Let me just remind you. So you could do it the way we did before. I'm just gonna, but I'm gonna do it this way because this is gonna be more related to Green's theorem. Remember we said if your function had the form p comma q, and then you multiplied it with d, dr, that you could write it like this, p dx plus q dy. And so in this case, what do we get? We get y dx, right? Plus minus x dy, okay? And then let me pull out to the side here. So what was our cosine sign? So our x is this cosine, our y is sine. What's dx then? Negative sine t, and dy cosine of t, right? And so we end up with the integral from 0 to 2 pi, and then just fill these in. So y is sine, dx is negative sine dt, minus x was cosine, dy was cosine dt. So what's that give us? Negative sine squared minus cosine squared, so that's just -1 dt, and so you end up with -2 pi. Make sense? And let's see. Yeah, and then, so maybe I won't draw in a bunch of them, but take this vector field. What if we're at this point 1, 0? Where are we pointing with that vector field? So this is our curve we're moving along. Here's my vector field y, negative x. So if we're at the point 1, 0, what's f?
Zero, one. Not zero.
0, negative 1, right? So that's the vector pointing down 1 unit, right? What if we're up here? So that's
One,
0, 1. So it's 1, 0, right? Like that. What if you're here? So don't worry about the exact value, but it's negative, right? They're both negative and the same, right? So then I have a negative y and a positive x. So I'm moving in the negative x direction, right? And the positive y direction. So I'm going to be moving like that. Does that make sense? And so you can see, right, we ended up with a negative value for that integral. And you can see as we're moving along the curve this way, our vector field is pushing against us, right? And so we should end up with a negative. We should have expected that negative value. Does that make sense? Then if you went around with a positive orientation, you can see this vector field be helping you move around the curve, and you'd end up with a positive value. I mean, see, with a negative orientation, right, the other direction around. Okay. Anyways, for right now, that was just that, and then I think we'll maybe just do this one with Green's theorem real quick. Well, maybe not. We'll see how messy it is. So let me just state Green's theorem. Okay, let C be a positively oriented piecewise. There'll be a bunch of little conditions here that, again, we don't need to use all that often or worry about all that often. Piecewise smooth, simply closed curve, simple closed curve. In 2 dimensions, and let D represent the region enclosed by C. Okay. So here's our theorem. There's the setup. And I never explicitly defined simply closed, I mentioned it, but again, this is simply closed. That is not simply closed, right? You can't cross back over yourself. So when we talk about this, we want to be defining one region. And you even have to be careful if you come back and sort of kiss yourself for a second. That's not good.
I want to ask, what
Yeah.
is the second line, CR or CB?
Where are we at? Here?
Second line, CRIE, well, T.
This here?
Oh.
Where? Oh no,
Second
oriented.
line.
That's the O.
Oh, yeah.
Oriented.
Okay.
Sorry. Every letter looks like the wrong letter. Is that better?
Yeah, thank you.
Yeah. So again, just means we move around it. Now we can, so this theorem will only be for positive orientation, but remember, if you have a vector f dr and you negate the orientation, so you go backwards, then you just get negative of the other one, right? And so if we ever have negative orientation, we can always just make negative the integral we want. So we'll always be able to use this regardless of the orientation, but you have to be careful because you'll get negative signs. So here is the setup then. So if P and Q have continuous partial derivatives, in an open region, containing D, then, okay, so the line integral over C P dx plus Q dy, and remember that's the same thing as f dot dr, right? It's just another way to write f dot dr, is equal to the double integral over the D that you're after, and then Q sub x minus P sub y dA. And I guess, I don't think I'll, so notice, if you had a conservative vector field, right, and we're on a closed loop, we know that answer should be 0. Your test for whether a vector field was conservative was whether Q sub x equaled P sub y. So if it was conservative, this would be 0, right? So it wouldn't even matter what you're integrating over, you'd get 0. So at least that confirms everything we think should happen. Let's look at this example that we had then. So we had, what was our, so it was y negative x, is that what it was last time?
Yeah.
F. And then we're over the circle, right, unit circle. And we were going with positive orientations, we're heading this way. And so we want to compute this y dx minus x dy. So again, there's your P, there's your Q. And so the unit circle satisfies these conditions, right? It's positively oriented, it's smooth, and it's simply simple closed curve. This function is continuous everywhere, and so is its derivative, and so you don't have any worries about that stuff. So now let's just apply Green's theorem. So what does Green's theorem say? That we should be able to compute this integral by doing the double integral over D, which in this case is our circle, right? So the C is the boundary of the circle, the D is the inside of that unit circle. And then, I'll just write it out, Q sub x minus P sub y dA. So in this case, what's Q sub x? Negative 1, P sub y, 1, so negative 2. Is that okay? Over R, over D. And so if you then, so you can do this in multiple ways, but now we have a double integral, right? And so we're integrating negative 2 over the circle. So what's the best approach to do that? Switch to polar coordinates, right? And so when we do that, what do we get? Negative 2 R dr d theta, and the unit circle, r goes from 0 to 1, 0 to 2 pi. Good. Integrate that. Negative r squared, 0 and 1, right? So 1 will go in, so you'll get -1, you'll get that negative 2 pi back. Does that make sense? Okay, so we'll do a few more examples next time of Green's theorem, but that's essentially the idea, right? And it can be really useful. Now, there's times where the double integral could be much worse than the line integral, and so sometimes we'll work in the other direction. We'll have some nasty double integral that we want to work with, and we'll say, oh look, we could make it this nice line integral and go from there. But we'll finish that next time. So.